Welcome everyone today. Last week we introduced homogeneous coordinates, and in this lecture today we will actually use them more extensively than we have done that before, because what we are aiming at doing today is describing the process of how a point from the 3D world is actually mapped into my image. And this involves things like where the camera is in the world, where the objects are in the world, but this also involves kind of the internal parameters of the camera. And these are things which are called extrinsics and intrinsics. So extrinsics are a set of camera parameters which describe where the camera is in the world and where it's looking to. And the intrinsics are the kind of the internal parameters of the camera. So things like the camera constant or other elements of that camera which have an influence on how a point from the 3D world is actually mapped to the image plane. And the goal for the lecture of today is that you completely understood the process of how a point from the 3D world ends up being at a certain location in my image, what kind of different cameras do we have, what different assumptions are involved in terms of distortions, maybe even getting an idea on what typical distortions look like and how we can actually model them, and also get an idea of what we can tell about the object in the scene given we have a point mapped to a certain pixel location. So the overall process starts, we have the 3D world, we have a camera which takes an image of the 3D world, and that's kind of the output image that we get. So what we want to do is, or one of the motivations for the work is we want to estimate the geometry of the scene. And in order to estimate the geometry of the scene, we need to understand how points from the 3D world are actually mapped to my 2D image plane. And there are several coordinate systems which are involved in this process. And we have to now go through 4 different coordinate systems that we will actually use or will map between in the lecture today. So the first thing is we have an external coordinate system, or the world coordinate system, or object coordinate system, which is kind of an externally given coordinate system. This is the first thing that we have, or Objektkoordinatensystem in German. The second thing that we have a camera coordinate system. And this means how the camera sees the world. So everything is described relative to the location of the camera. So the pinhole model relative to the pinhole. So the pinhole is the origin of the camera coordinate system. So the mapping between the world coordinate system and the camera coordinate system is typically a rigid body transformation. Of course, it's just a shift in 3 dimensions and a rotation. Then the next thing which happens is actually, from the camera's point of view, we map the 3D world to the image plane. And this is the image coordinate system, or image plane coordinate system. And then finally, from the image plane, that's mapped to the sensor of my digital camera, or onto the film in the analog days. But we are looking here into digital cameras. For analog cameras, we actually have one system more. For digital cameras, we map that finally to the sensor frame where we have the individual pixels. And say then this pixel corresponds to whatever certain direction of the 3D world. We now have to deal with these different coordinate systems. And if you look to the different quantities which are involved, so we have the object coordinate system. This is a 3D coordinate system, so a point in the Euclidean 3D world is represented by x, y, and z. And these are all capitalized because, according to the notation that we use, this is something in 3D. Then we have the camera coordinate system, and they all have this superscript k over here. K from German camera. So this still living in the 3D world, but the k indicates that we're in the camera system. I could actually have made an O over here. That would be maybe more consistent, but then we'd have O's all over the place, and therefore, whenever there's nothing written, we refer to the world or object coordinate system. Whenever we are in the image coordinate system, now we go from 3D to 2D. That's where the central projection takes place. We are living in a 2D world on the plane. Therefore, there are lowercase letters, and we have the C here indicating that coordinate system. And then we have the sensor coordinate system. We again in 2D on the sensor, but the sensor is typically not perfectly in line with the sensor plane, or at least there's definitely an offset between them. So we have to map between those points. Again, if there's no index given, this means we are in the object coordinate system. Okay? So what we're doing now, we start in the 3D world, map it down until we end up at the sensor. And how we can actually describe that is in that way. So we start over here. We have an x, y, and z location of a point in the 3D world, the one for doing everything in homogeneous coordinates. Then we have the mapping from the object system to the camera system. So this basically describes where is the camera in the 3D world. Then we have the second transformation over here, which says, okay, given the pinhole is the origin, and actually I'm looking into the direction orthogonal to the image plane, this transformation maps the point onto the image plane. And then we map from the image coordinate system to the sensor coordinate system. And then we end up getting a 2D point in 2D, the third dimension, for the homogeneous coordinates. And again, so we go from 3D to 2D over here. And in here, we actually go down from 3D to 2D due to the central projection. So there are different steps that we are taking into account now. I want to go through all those steps, and it's important to understand those indices. So sensor, the camera, plane, the camera itself, and the object system. So we have to deal with those different coordinate systems over here and map between them now. Okay, just one further illustration to hopefully make that more clear. X, Y, Z, a world coordinate system or object coordinate system. Then we have the camera origin over here with X, Y, and Z. Then we can map that to the image plane. The image plane is this one over here with a principal point over here and the X and Y. And then we have the sensor system because the sensor is definitively shifted with respect to the principal point. So 0, 0 in the sensor system is not the center of the sensor. It's the first pixel, for example, over here. Okay? So there is a relation between those coordinate systems. The first thing is this transformation between those is typically an arbitrary transformation because I can take my camera to every point in the world and can take an image. Between the camera system over here and the image system. So given that we assumed this is the line perpendicular to the image plane, and we have the x-coordinate is aligned with my image plane. So this x-coordinate is aligned with this one, and this y-coordinate is aligned with this y-coordinate. And the distance here is exactly c, my camera constant. So this point over here, the origin of my image plane coordinate system, is very strongly linked to this coordinate system. So the direction of the x-axis is the same, the direction of the y-axis is the same, and they're all at 0, 0. The only thing is that it's kind of the z-coordinate in that system is C, where this is the center point. So we can label this. So those two guys point to the same direction. It's basically written over there. Those two guys point to the same direction. So this point here, expressed in this coordinate frame, is actually at 0, 0 for x and y. The only thing is, in the z direction, I'm moving, have a distance of c. So the coordinate system of c, of my image plane, expressed in the camera frame is 0, 0 minus c. Right? So there's a fixed transformation between them. So they are strongly linked. And of course, we also have a fixed link between the sensor, so the image plane, and where the sensor is actually mounted. So this is where the image coordinate system is and where the sensor sits, because the sensor is installed in my camera. So this is also some of the parameters which typically do not change. Because the chip is basically glued to the back of my camera unless I change the lens or do a serious setup change in my camera, this should actually stay the same. Or actually, the location of the sensor in the camera should not change even when I change my lens. Okay? So this is completely free and can change from image to image. The other things hopefully don't change from image to image. Okay, sorry. We can also express it in this way. We have from the object coordinate frame, we can map to the camera coordinate frame. And this is something which works in both directions because it's a rigid body transformation. So the first thing is from the object to the camera coordinate system. And this happens all in 3D. Then the next thing is when I move from the camera coordinate system to the image plane, this is actually the ideal projection or the central projection which maps from 3D to 2D. From the 3D world expressed in the reference frame of the camera onto my image plane. Then we map from the image plane to the sensor. Everything happens in 2D. And then there's something which I haven't talked about. We still stay in the sensor frame, but there's an additional transformation that we actually do over here. And this is for accounting for other nonlinear errors. So everything happens here kind of as a linear transformation. And then there are kind of things like errors in my lens, like barrel distortion is one of the prominent examples, that I want to handle with an additional transformation, which is a nonlinear transformation, which describes additional errors. But kind of the standard process, if we have kind of the perfect lens and only linear errors, we could actually stop over here. And a lot of things only go up to this point. But if I work with real cameras, I actually have to take these elements into account. And the first part over here, so this part over here, are the so-called extrinsics. So it's kind of the external configuration or the configuration of the camera with respect to my world coordinate system. And here we have the intrinsic parameters or intrinsics, which are internal or special to that camera and which hopefully don't change or don't change rapidly, don't change from image to image. Of course, if I change parameters in my camera or change the lens, it would of course get a different camera constant or make it a different one. And these are the intrinsics, and these are the extrinsics. So this is the pose, and pose refers to position and heading of the camera. The extrinsics and the intrinsics are kind of the internal cameras, which tells me how the object in front of the camera is actually mapped to the sensor. Yes, please.
What happens if you refocus your camera with the intrinsic parameter?
Yes, so you will change your focal length. And you will basically change the camera constant in the way as if you have a zoom lens, for example. You basically, so it's not very easy to actually express this because you don't know exactly where the center is if you have multiple lenses. But what you basically change, you change your camera constant. And so this is a change in this part over here. So of course, if you have a zoom camera, this may change from pixel to pixel, but hopefully the other parameters, how your chip is glued inside your camera, should not change. Yes, please.
Where do you catch the discretization effects? I mean, you go from the linear to pixel.
So I'm not changing any discretization effect in this transformation. So what we're actually doing here, so even in the sensor system, we do not discretize. So we even have to do sub-pixel estimation. But of course, the intensity values that I get, they are in the end discretized and also quantized, as we have discussed this in the beginning of the course. But in this kind of mapping, where a point from the 3D world is mapped onto the sensor, that is something which is not discretized in here. Okay, so any further questions about the overall setup, what we're going to do today? So we start from here, move down until we are here, and we actually turn around and try to go the way back. So to get the mapping from one side to the other side. This will take much longer. The other one will then be rather quick. But of course, there's a loss of information on that path from the left-hand side to the right-hand side. So we won't be able to recover all the information. Okay, any questions up to that point? Yes, please. Yeah, that's exactly what I said. So how can I go back? So if I start from here, from 3D, I move to the 2D world, there's a loss of information. Some of those errors I can actually, the error works on the other side because the transformation is invertible. So I can go back, but definitely in a step from here to here, I can't recover all the information. But I still can say something about the object in the world. And we will see what we can actually, how we can actually invert this process, and that we definitely won't find a unique solution, but we can actually see the solution space and can actually nicely relate them, for example, to the camera parameters that we have. Any further questions so far? So it's not the case. We start with this block. As I said, we start from here, going down to the other side. So we start with the Extrinsics, or äußere Orientierung. Well, that's actually a pretty easy task to be done. So what the Extrinsics describe is where is the camera in the world in terms of pose and heading. And this is a rigid body transformation, and that is invertible. So if I know where the world coordinate system is, I know where the camera is. I can estimate in both ways. So where is a point, how it should be seen from the camera, and if I know where the camera is, I see a point, I can express where it's in the real world. So how many parameters are needed to actually describe this transformation for the Extrinsics then? Yes?
6.
Exactly. I need 6 parameters. We need 3 for the pose, x, y, z, and 3 for the orientation, for the heading where the camera is actually pointing to. Okay, so that's not very difficult. So it's something which should be a known concept. So let's start and say, okay, we have a point in the real world, point P. Let's see where this point ends up with respect to the camera system. So we have our point, xp, x, y, and z coordinate. So the P just refers as my point P. And I know the location of my camera in the world coordinate system. So where the pinhole, at which x, y, z location is the pinhole in the world reference system. And this is xo, yo, zo. So 3 degrees of freedom. Okay, so I know where this is simply the location of the camera in the world. And I also I said we need to know the heading where the camera is pointing to, and this is something which we typically encode with the rotation matrix. So which maps from the object coordinate system to my camera coordinate system. And then we can actually describe the transformation that a point xp in the world coordinate system is mapped to a point xp in the camera coordinate system, so relatively seen from the camera, giving this transformation. So we just subtract the origin of our camera and then apply the rotation matrix. So the point is mapped from the object coordinate system into the camera coordinate system. So everyone happy with this equation over here? Yes, please.
Sorry, I didn't catch what is what. So it starts with x0, which is the
Okay, no.
camera itself.
Okay, yes, so x0 or xo is the origin of the camera. So it's the location of the pinhole expressed in the world coordinate system. So if my world coordinate, this is the center of the world coordinate system, and I'm here with my camera and the camera is pointing to you, that would be whatever, x 80 centimeters, y again 80 centimeters, and upwards 60 centimeters. So this actually, that's the focal point. This is this guy over here. And what we want to describe is how this point, which are you, the object point over there, is mapped from the world coordinate system, so with respect to this point, how it is seen from the camera, so from this point over here. And what I also need to know is actually where the camera is pointing to. So am I pointing to the ceiling, to the ground, or towards you? This leads to a different coordinate expressed with respect to my, my origin. And this is expressed by the rotation matrix. So if I want to map you from the world coordinate system to the camera coordinate system, I take your coordinates in the world coordinate system, subtract this location, the location of the camera, so the difference here, and then the appropriate orientation. And then I obtain your coordinate expressed with respect to this point over here. Any further questions? Okay, so this was done in Euclidean coordinates. Let's do that in homogeneous coordinates. Exactly. So this is a point. This was my point in Euclidean coordinates. So I expanded the vector. Then this can be expressed as a rotation matrix. No translation. no parameters over here, which would lead to the projective transformation. Then I have a second transformation, which is just a shift, which is no rotation, so a 3 by 3 identity matrix, 0 over here, 1 over here, and here then minus the location of the origin of my camera. And here I have my point in the world coordinate system expanded by 1. If I want, I can multiply those two matrices and get this transformation over here. With this transformation over here, I can actually express this very compactly as we have written that in the beginning. So the point in the world coordinate system P through this transformation H from the object frame to the camera system, giving me the point in the camera system. And then this transformation matrix is exactly this matrix over here. So this is expressed in Euclidean coordinates. This is expressed in homogeneous coordinates. So this one is slightly slanted to the right, the font. This one is not slanted. So for the capitalized characters, it's harder to see it for the lowercase characters, but everything which is non-slanted or non-italic is Euclidean homogeneous coordinates, and everything which is slightly slanted, like this character over here, is in the Euclidean world. Yes, please.
Could you, when it's applicable, say something when do you actually multiply matrix from the left or the right? Because that was something which I sometimes confuse with the Förstner method.
So matrix multiplications are not commutative, so I cannot change the order. But if I first multiply those two matrices, or if I multiply those 2 points, this doesn't matter. What I've done in here, so this is not a matrix, this is the point. This is my input point, so the point in the world coordinate system. And this is my translation, and this is my rotation. Because what I do is, if I have a point, I first, so what this was the offset of the camera in the world coordinate system. So I subtract that because then I do the rotation with respect to this point over here. So this is the order in which I have that. So if I can either multiply this point first with this matrix and then the vector which is the result with this matrix, or I can multiply those two matrices first, which gives me this matrix, and then multiply it with this point. This doesn't matter.
Okay, what sequence, what do you do first? So you first do the translation and then do the rotation.
Yes.
That's why I go from right to left.
Yes. Yeah. So from here to here. Okay, any further questions at that point? Okay, but that's it. We're also done. So we've specified the transformation from the world coordinate system to the camera coordinate system. It's a rigid body transformation, 6 degrees of freedom, and it's clearly invertible. So that part is done. Let's look to the intrinsics, or the innere Orientierung. So this is all the remaining part. Now we have our point expressed in the reference, in the coordinate system of my camera, and now we need to map it first to the image plane, and then we need to map it to the sensor. Okay, so we again here, we start over here to this transformation to the sensor and then account for the nonlinear errors. Again, some of those transformations are invertible. So I can map, if I'm on the image plane already, I can map to the sensor forth and back. Also here I can map forth and back, given the knowledge of my nonlinear function, of course. But there's a loss of information here. And this is due to the central projection. So mapping from the 3D world to the 2D world. Okay? So how that works? Don't want to go into the details, but we typically have our image plane, well, the sensor is mounted in this image plane. There's some point here, which is the principal point. And so this is a 90-degree angle over here. And this is the direction of the camera, where the camera is looking to. And then I have a distance between the origin of the camera, which is this point K1 and K2, which is typically assumed to be the same point for a thin lens, then the image plane, so distance from the origin to the principal point, is exactly my camera constant c. In the perfect case, this is actually the optical axis, and the direction where the camera is pointing to is actually the same, but here it's drawn as a small deviation. And all the other points, all the other elements, we're currently not that interested in. But if we have a point, P, from the 3D world, which is mapped onto my image plane first, and then there is a correction for that in the end based on the location of the sensor and based on the errors that my system may have, so the nonlinear lens errors, which I do as the last transformation over here. Okay, let's go into the details. So we split up the overall process into the projection on the image plane without considering any errors that we have in there. So we use an ideal perspective projection to map to the image plane. Then the next step, we count for the fact that where the sensor is mounted on the image plane. And then as the third step, we compensate for the other errors. So here again the points. So P was the point in the world or in the camera. Everything which has this overline over here is on the image plane as a sensor, and the primed variables are those variables which take into account the nonlinear errors in there. And again, our assumptions was we have a distortion-free lens. The focal point and the principal point lie on the optical axis, which is actually not. Well, I wanted to say it's not true, but it is true because this is for the first step. So this is for the ideal perspective projection. In the first step, we assume that this is the case. And then we compensate for the fact that this is in reality not the case. All rays are straight lines and path through the K1 and K2, so they're exactly the same points. And this defines the camera coordinate system, and the distance from the camera origin to the sensor plane is my camera constant. Now there are two ways how I can actually describe that. So if I have the origin of my camera, I can kind of use the physically motivated model, how this is actually done in reality. So we have our point here in the real world. The ray passes through the origin of the camera and is then mapped to the image plane. And in this case, the camera constant is in the positive z direction of my coordinate system. So c is larger than 0. Or I take something which is often used in image processing and computer vision, where we say, okay, we basically just flip the image from this side to the other side. So then we have the origin, and the point P prime is on the negative side of the z coordinate. So on here, so I can see that this point is actually projected onto this image plane. And then the image also stands not upside down as it would be the case here. Things work exactly the same way, just once one point C is larger than 0 or C is smaller than 0. And we actually stick here with this one. Again, the equivalent is just a rotation of the image plane around the origin by 180 degrees. So did I say it was flipped before? That's not true. This is the rotation, so I'm rotating like this over the image plane over here. But the rest, the mass stays exactly the same. So we use this approach with a camera constant smaller than 0 throughout this course. Okay? Just C is negative. It depends if, C is a distance or distance with the vector, but we use C smaller than 0. Okay, so let's go through the projection. The projection is directly obtained through the theorem of intercepting lines, or Strahlensatz, as we have done that already in the matching chapter for a single camera. So we have our point in the we have our point in the camera coordinate system. Where this point is mapped to depends on the camera constant, and it depends on the distance of the point to the camera, so that coordinate. So if I go back one slide, basically have this example over here. So this is my point P in the real world. It's mapped into the P bar over here on the image plane. And either, so if this point moves further away, so it moves here, the point will get a smaller x coordinate the further it goes away. Or if I change the camera constant, depending on where it moves to, this element gets larger or smaller. And just through the theorem of intercepting lines, I can compute that my image point is the point in the 3D world, the x coordinate of the point in the 3D world, divided by its z coordinate times my camera constant. And this gives me the x, and the same way for y, the y coordinate. I can do the same thing for z, but I then have that divided by z here, which directly gives me c. So the third coordinate is always mapped to c. So this is, and this makes sense because this is the distance from the origin of the image plane. So if it would be in 3D coordinates, the third coordinate would be c, but I'm actually kind of, because everything, all the depth values are mapped to my camera constant. And this is what describes this projection over here. I can now express this in homogeneous coordinates. So my 3D homogeneous coordinates, I apply this transformation matrix C, C, C over here, which maps it to the new point. And then I need to do just kind of just the scaling, just the scale through phi. And then what I do is I drop the third coordinate in here, so this line over here, because the z coordinate gets eliminated and everything is mapped to C. And then I obtain this matrix, which is the same matrix as this one, but just the third line is actually missing. So then we have our 4 coordinate vector over here, which is projected to the 2D world. So then I get 3 components here in homogeneous coordinates, which define me the projected point in homogeneous coordinates in my camera coordinate system. Is it clear? So what we have done, we've done one step which was scales down our image according to the camera constant, and then we eliminated one dimension. Of course, we map from the 3D world to the 2D world. And this is just applying, if we now apply this transformation over here, we get exactly this result. So is that kind of, yes, please.
So in the first matrix of the C's,
Yeah.
why is the one not in the right
Oh, that's absolutely a mistake. This one should sit over here. I'm sorry. I'm very sorry. So this was a LaTeX mistake when I was making this equation. This one must be here.
And in the matrix below, is it the same? Or
Oh, wait a moment. No, maybe my...
Because otherwise you get a Z component now, which you don't want.
Yes, this is copy-paste mistake. I'm very sorry. See if the copy... Okay, let's check. Let's check. Let's apply. So this is the final one. Let's check what happens if I multiply this matrix with this vector over here. So the first component will be C times x k p, right? Multiplying this one with this guy, next one with this one with this one, this one with this one. So we have C times y k p. Now this one with this one I obtain z. Now I think it's correct. So I just get zk p over here, which is my homogeneous vector x p c, right? If I now normalize this vector, because in homogeneous vector I divide by the last component, so what I get is c x k p divided by z p k c times k x P divided by K, Z, P, and 1. And this is, if we go back, exactly the results that I have over here. So I'm happy. That coordinate is gone due to the projection. We just have those two coordinates, which are the correct ones, expanded by 1, so already normalized. So we get exactly this result. So what's written over here is correct, so the 1 must be here, not here, and the same here. So it's correct what's written on here. Sorry for the recordings, sorry for the confusion. But at least now, from these calculations, you should have seen that this exactly gives me the result of the theorem of intercepting lines. So it wasn't too bad to do the calculation. Okay, any further questions? Okay, so what we have, we can again, in the homogeneous coordinates, express this transformation quite easily, saying my point from the camera coordinate system via the matrix P, which maps from K from the camera to the image, which is exactly given like this, gives me the point, the projected point in the image plane. Okay, so now I can actually combine that. I can say, okay, given I have the ideal camera, which just does the ideal projection, I can now combine this matrix with the transformation we had before from the world coordinate system to my camera coordinate system. I can say, okay, this is now P mapping from O, from the world coordinate system, to the image plane. So it's the combination of the extrinsics and the projection that we just have done, which is given as the transformation we identified. This was the rigid body transformation, so this part over here, and our matrix. We just multiply those two guys. We actually have the mapping from the world coordinate system to the image plane. Okay?
Well, from the formal point of view, you can't multiply those.
I can. This is a rotation matrix. This is three-dimensional. So this is what's transposed. So this is 3 elements, and this is a 3 by 3. So this is a 4 by 4 matrix, and I can multiply the 4 by 4 matrix with this guy. But good that you raised that, because it will also come very, very soon. And as a result of that, we can actually express this matrix here as a calibration matrix for the ideal camera, where only the camera constant matters, but nothing else matters. So something which is called the ideal camera. And then we can actually write the combination of this calibration matrix and the projection and the exterior, the extrinsics, in one way. So this matrix P as KC, so this calibration matrix, and then kind of this weird form. Have you seen this weird form for writing a matrix with this bar over here? That basically means we are just stacking together different elements. So we are stacking this rotation matrix, which is a 3 by 3 matrix, with a vector. This bar is just written to kind of clearly separate the block matrix and the vector over here. And this is just minus r times x0, so it's a 3 by 1 vector. I can also multiply the rotation matrix out of this, then this turns into the identity, and here's just minus x0, so this one. So these elements here are 3 by 4 matrices, because this is a 3 by 3 matrix, and this is a 3-dimensional vector. Also I've written that up here, what that means. This is exactly the same as what's written here. So this is a 3 by 3 matrix, in this case the identity. So this is this identity matrix over here. And this is a vector, which is given by this vector over here. This is what this notation stands for. It's very frequently used because you can quite compactly write matrices which are stacked together from different elements. So it's just kind of just for making the notation easier, and how I can stack the matrix with a vector. Okay? Okay, good. So what we have is exactly this form over here. Using this K is always a calibration matrix, because it resembles the idea of the calibration matrix is to model the intrinsic parameters of my camera. So this matrix will get more and more elements through this course, or through the lecture today. Okay, so given this transformation, we can map any point from the 3D world onto my image plane, expressed in homogeneous coordinates, everything in here. If we would write this down, we actually would get this element over here. So this is the calibration matrix, this is my rotation matrix, and this is multiplied with the identity, and then, so those elements already computed. Then I get this one over here. So if I now turn this into Euclidean coordinates, that would be actually the result of the Euclidean coordinates, with these, all the different elements that I have in here. If you're going to do the derivations all in the Euclidean coordinates as it's done here, you're, I guess, more likely to make a mistake compared if you use all the homogeneous coordinates as in this form over here. Of course, the transformations can so nicely be chained, which is one of the big advantages for really simplifying the mass over here. At least if you write it down on a piece of paper, you're much less likely to make a mistake. But these are so-called collinearity equations for mapping my point from the world coordinate system onto for the ideal camera onto my image. Okay? So where are we in the process? This is done. This is just what we just did. So we are somewhere here in the intrinsics. And what we had so far, this was the rigid body transformation. This was our central projection. And there are two things which are missing over here. So we now will add two more things. An affine transformation, which then gives us a so-called affine camera, because the mapping here from the image plane onto my sensor is an affine transformation. And then we have, due to some errors like lens errors, we have nonlinear effects or nonlinear errors we add additional here. What we now do, we actually move from here to here and now continue this process towards the end. Any questions up to that point? Okay, if that's not the case, let's make a 5-minute break. Let some potentially warm but at least fresh air in, and then continue.